Homework pressure? No more. At Spring Library, we explain every topic in simple way. Join the learning family and score high every day.
Okay, for this problem, we're drawing a position versus time graph of a runner who's running for 40 seconds to try and complete a 100-meter race, and every 10 seconds, the amount of the race they finish is half of what's remaining. So we're going to draw kind of a sketch of this position versus time graph. So on my x-axis, I have the time, and on the y-axis, I have my position. Now, since this race is going to 100 meters, I'm going to mark the top of my position graph as 100 meters. And all the way at the beginning down here, we have 0 meters. So I'm going to put some time intervals. We have 10 meters or 10 seconds in, 20 seconds in, 30 seconds in, and 40 seconds in at the end of the race. And going to kind of draw these up here to keep us focused on what we're looking at. We need to know the 10, the 20, the 30, and the 40. Now, what the problem tells us is that every 10 seconds, the runner completes half of what's remaining in the race. So initially, the runner starts at 0, and there is 100 meters left in the race. So the runner is going to go half of the way there and travels actually the full 50 meters. Now, in the next 10 seconds, the runner slows down a little bit and only covers half of what's remaining. So half of 50 gives us 25, meaning this runner is only going to make it to the 75-meter mark over the next 10 seconds, so losing some steam. Then there's 25 meters left, so the runner travels only half of that as well, and we hit 87.5 right here. And then with the 87.5 mark left, there's only 12.5 meters left, so the runner finishes half of that and finishes at 93.75 for that final point here. Again, that's 93.75 meters. So the position versus time graph, because this is all constant velocity, we don't know anything about any accelerations other than they abruptly change for each of these 10 seconds. We're going to connect my points. Now, most likely this is going to be a constant acceleration curve where they're slowing down as they're running, but we don't know enough to do that. So we're connecting it with the straight lines here. Now, looking at this graph, we can see that the runner is slowing down over time because the slope of this graph is getting less and less, and the slope of a position versus time graph is equal to its velocity. So I'm going to draw our velocity versus time graph now. And kind of opposite how you would think about it, as our concepts get more complicated, like velocity is a more complicated concept than that displacement, the graphs get simpler. So since the slope of that position versus time graph is equal to our velocity, the first section where we were going 10 seconds, 20, 30, and 40, that first section where we were just going 10 seconds, to find the velocity, we would do the slope of that line. So the rise of 50 divided by the time of 10 gives us a velocity of 5 meters per second. Then the second chunk, they only go from 50 to 75, so it's going half of that distance in the same 10-second span. So the velocity from 10 to 20 drops to 2.5 meters per second. The next 10 seconds sees that cut in half again to 1.25 meters per second, and the last piece gets cut in half one more time to 0.625 meters per second. Now, this graph is not very realistic because we have kind of these gaps where the velocity abruptly changes, and that's probably not what's actually happening. As you move forward with this concept, you'll get into what acceleration graphs look like, and that would add us another layer to look at. But until then, this is a good approximation of what the position versus time graph looks like and what the velocity versus